Hello and welcome to Chapter 3, Foundations of College Chemistry lecture. I'm going to be going over elements and compounds. As before, if you need to pause the video to stop and write notes, feel free, but I will be going through this PowerPoint pretty fast. I'm also going to be sending you in additional resources to learn the material. Alright, let's get to it. So here's the chapter outline. We're going to be talking about elements, their symbols, their names, the distribution, what types they are. We're going to introduce the periodic table, how it's organized, and then section 3 is all about compounds, compound names and formula, and how do we write molecular and ionic compounds. Elements are the fundamental substance, and they cannot be broken down any further. Copper is copper. You can't take copper, the element, and change it into anything else. They're pretty much the starting of all matter, whether it be a metal with a nonmetal or a metal to a polyatomic ion to make various compounds. The individual elements is the building blocks, the individual pieces to a compound. Conversely, atoms are the smallest unit of an element. We're talking the subatomic particles. Take, for instance, carbon. Carbon is an element, but the atom of carbon includes 6 protons, 6 neutrons, and 6 electrons. Unless you're talking about different isotopes of carbons, then the neutrons can change. So specific number of neutrons gives you what isotope of each element there is, but fundamentally the atomic number of the element tells you the number of protons and electrons in the element. Here is some elements that you need to know, but with that, you need to know 118 different elements. There is a periodic table you will get on the final, but also on my test. So I'm going to pause the review of the notes. Here is the periodic table. This is right from the chemistry department. This is the final exam periodic table handout. Notice how there is an atomic number, there's an atomic symbol, and an atomic mass, but there is no name for each of the atomic or the elements of the periodic table. You will have to memorize the majority of this table. I've seen the final have zirconium on it. I've seen the final have silver on it, cadmium, mercury, gold. So you cannot say, oh, I only need to know the first 18 elements or the first 36. You need to have a handle of the entire periodic table. Will we go past element 80? Probably not, but 82 is lead. Lead is very common as far as in different compounds and questions. So just be aware that you need to have a handle on the periodic table. I will be sending out a couple of different websites to you to help you learn the names to the symbols. One of those is one that I've used year in and year out. It's JLab. Again, you don't have to worry about pausing the video. I will send this link out to you. But I would start small. Don't try to do all of the periodic names or symbols. Start with like 5 or 10 to begin. And I'm going to kind of briefly show you how this works. I accidentally hit additional options, so you could just study the first 20 at first, the first 36, so it limits it until you get a handle on it, right? So let me clear all sections, and it's not letting me, so I'm going to do all solids, all liquids, all gases, so it just includes everything. So this particular game is asking you to type stuff up. It's going to flip back between what's the element name, what's the element symbol. So I'm just going to type something to show you what happens. Let's say you think this is hydrogen. Check my answer. Nope, it's not. It's disopronium or disoprosium. Sorry. You could click tell me more about it. After a few questions, how am I doing? It'll give you kind of a percentage, all right? And then you can just go on to the next one. I know this one, but I Again, you have to spell it correctly. So I'm going to try to get as close to it as possible, but let's check the answer. It will mark it wrong if you spell it wrong. So it's kind of close, but I forgot the S here. It's not GA, it's GN. So just be aware of that. This is a game that you might want to play maybe after you do the other game that I'm going to send. So this is by Encyclopedia Britannica. The reason why I like this one is, yes, there's a timer bonus, but it's more you're picking the elemental symbol or name based on what it gives you. So let me show you how this one works. So here it's got FL, and you have to pick what name goes to that symbol. Okay, so Florilemorium, all right? Then you click next, DY. Well, we just did that. Saprosium. XE, sorry, Xeon. Okay, and then let's say, oh, I think this is Nobilium. Oh, then it gives you the correct answer. It also, I wouldn't worry about your score or your time, but it'll keep going over the ones you got wrong. Is the point. You keep going, and it will pull back the ones you got wrong, so you can review those again. So let's, maybe I think this is cobalt. No, it's chlorine. Thulium. Maybe I think this is rhenium. So you might be able to guess and get some. Well, K, maybe it's krypton. Oh, no, it's potassium. So don't make the mistake that the letter of the symbol has to be in the name. Potassium doesn't have a K in it, but krypton did. Don't think, oh, it's got to be krypton because it's the first letter. No, not necessarily. Here, only europium starts with UE. Sometimes that works, but other times it doesn't. So like AT, you would think, well, none of them start with AT, so which one is it? Is it this one with T? Is it this one with T? This one doesn't have a T. So is it arsenic? So try to do your best, okay? And if you guess wrong, it'll keep bringing these back, okay? So I will give you those two websites for you to be practicing. I like the Britannica one because it gives the symbol and you have to choose the name. It keeps going over the ones you missed. All right, so please do know that there are 11 gases. There's 2 that at room temperature, all elements are solid except for the 2 liquids, bromine and mercury, and the 11 gases. Here's some common elements, but again, you do not need to memorize, how much are in the Earth's crust. I'm not going to test you on that. That's not on the final. Now this one I've seen on the final sometimes, so I do put this on my test. I might ask what accounts for 20% of the atmosphere, what accounts for what's mostly in the sand and soil. I might phrase that question multiple different ways. I might also ask you what is the second largest element in the Earth's crust? Well, the Earth's crust would be oxygen and silicon. I'm not going to ask you all of these, like what's the least amount, fluorine, but I would expect you to know, like, oxygen is the most abundant on Earth, silicon would be the next most abundant. Elements in the human body, again, oxygen is the largest. You should know that because we're about 72% water. So oxygen's going to be there a lot. Hydrogen has to be there. Carbon is in our bones along with calcium. Okay. Name of the elements. I'm not going to really test you on did this come from a Greek or Latin word or German word. Who was it named after? Just understand that there are what's called ancient elements that were known by the ancients or philosophers like Plato and Socrates. That would be the ones that the actual letters in the symbol don't match the name. Gold is AU because of its Latin name. Silver is AG because of its Greek name, I believe. So I know sodium Na is natrium, and it's called, sodium because, of how it was discovered. but it doesn't match the Latin name natrium. So that I'm not going to test you on. You do need to know symbols. You do need to know names. First letter is always capitalized. Second letter is always lowercase. You need to know that information. Right? Again, you need to learn the periodic table and the names and the symbols of the elements. So this is just what this is going over. I don't want you to copy these tables into your notes. You're going to get a periodic table. You just got to learn to put the name with the symbol. All right. So again, be careful. Understand that first letter is always capital. Second letter is always lowercase. So if there's two letters and one is lowercase, that's part of that element's symbol. So take, for instance, cobalt, CO. Well, if you're writing something out, you need to make sure that you don't write capital C, capital O, which is carbon-oxygen bonded, versus the element cobalt. Okay. So here's an introduction to the periodic table. Like I said, you will get a periodic table. You will not get a periodic table. I apologize. Let me go here. It does give 1A, 2A, and then group 1 through 18. It gives those significations, but it does not put the family or group names on there. So if, I apologize, noble gases, this is the special name given to the elements that are in the 18th group, helium down to xenon. So you will have to memorize some of the group names. The groups up and down, the vertical columns here are called groups or families because they have properties that are very similar to one another. So I kind of explain to my students, the vertical columns are like your immediate family, your father, your mother, your siblings. They're closely related to you. That you have more in common with your immediate family as far as genetics, how you look, that kind of thing. The periods or the horizontal rows, those are your extended family. So you have some commonality with them. You might have a few traits from them, but these are like your cousins, your niece, your nephew, your grandparents. So, potassium, calcium, all the way to like zinc. Those are metals that are mostly white to silver. They're all in period 4, so they all have 4 shells. So they have some things that are similar to each other. But up and down vertical groups, they're called families because they're very, very similar. Okay? So group 18 is the noble gases. Here's like an overview of the names that you do need to know. Noble gases, halogens, transition metals, alkaline earth metals, and alkali metals. There is another group. It kind of runs diagonal. It's called metalloids or metalloids. Tomato, tomato. But that's boron. You get boron, silicon, germanium, arsenic, antimony, trillium, polonium. Really the big ones are boron, silicon, arsenic, and antimony. That really, metalloids have properties of nonmetals and metals. So like, boron's kind of powdery, it's brittle, it kind of follows carbon more. But silicon is more shiny, it's silver, kind of like aluminum. Germanium's the same way, but arsenic is kind of like a whitish powder. Antimony is silver, kind of shiny, I would say more like a dull gray, but it can be shiny if it's mixed with other things. Okay. Here's the periodic table just broken down as far as metals, metalloids, and nonmetals. So here, this gray area right here. So know the big overarching names for the periodic table and how they're classified, but you also need to know the individual group and this huge family name here. Excuse me. So here's some properties of metals. So pause the video if you need to. The biggest is they're solid at room temperature. They're very good conductors, shiny, malleable, and ductile. Metals readily combine with nonmetals because metals want to give up electrons and nonmetals want to gain electrons to become stable. So they readily form compounds. Nonmetal properties, they're not shiny. This is actually a picture of sulfur. They're very brittle, very powdery, very low melting points and densities, and they rarely conduct electricity. They're very poor at it. Metalloids, on the other hand, like I said, had properties of metals and nonmetals, so it makes them very versatile. I don't know any electronic equipment or things that we use in the medical field that does not have a ton of boron, silicon, or germanium in it. Your phone is a good chunk of silicon. So that's what makes up all these chips that are in our computers. So they're very malleable. They can be cut into shapes very readily. They also are able to take a lot of heat and a lot of stresses on them as far as heating up, cooling down, and still perform. So this is a practice. You can pause the video. I'm going to go through these fairly quickly because you're going to have those games to play to help you learn. Natural states of the elements, like I said, most of them at room temperature are solids. There are a few that are liquids at room temperature, iodine and, mercury and bromine, and then you have those that are gases. So air, the oxygen, we call it the oxygen that we breathe, it's actually air. It's a homogeneous mixture of different elements. It's mainly nitrogen and oxygen, but there's also gaseous water. If there wasn't gaseous water in the atmosphere, all of our throats would be red, raw, bleeding. So there is a slight amount of gaseous water. And you can't tell the difference between nitrogen and oxygen in the gaseous stage, so it is a homogeneous mixture. We can separate out the nitrogen from oxygen, and we do that every day when we're doing any kind of reaction with igniting air to pull out the nitrogen and reacting the atmosphere with different chemicals to form nitrogen and then use nitrogen with hydrogen to form fertilizers. These are the diatomic elements. There are only 7 of them. If you look at the periodic table, it is all of the halogens. It is hydrogen all the way to the left side of the periodic table, and then nitrogen and oxygen. So I kind of teach my students, H hopped over to N, and NOF down to I. So you've got this nice 7 right here that reminds you, oh, there's 7 diatomic elements, and then hydrogen's kind of over here. Okay, so H NOF down to I. So separating diatomic elements, they can be separated from each other in chemical reactions. Water, hydrogen, H2O, neither hydrogen or oxygen is diatomic once it combines. So if you have individual oxygens and hydrogens, are going to readily react with one another to form water. They can't exist on their own. Like, we can have individual atoms of iron or copper floating around in a solution, but hydrogen, the diatomic elements, cannot just be by themselves. They have to either be bonded to each other or they seek to bond out with other elements to be stable. All right, so section 3, compounds and formulas. A compound is a substance containing 2 or more different elements that are chemically combined in a definite proportion by mass. Compounds, unlike elements, can decompose or be broken down chemically into individual elements, individual atoms, if we go that far, but we can take water, apply an electrical source, and we can separate out the oxygen from the hydrogen, and then the individual oxygens will pair up, and the individual hydrogens will find each other and pair up. Okay? And it's always whole number ratios. You never have like H1.50. That you don't get a half an atom reacting with another atom. There are distinct differences between molecular and ionic compounds. The biggest one is that molecular compounds are held together by covalent bonds, and ionic compounds are held together by attractive forces of negative and positive called cations and anions. So here you see the picture of Na plus, Cl negative. You got a positive being attracted to a negative, kind of like a magnet, to form a compound. Here with water, you've got hydrogens here that seem to be like pushed away as far as they can get from one another, and it seems like they're on the side, and there's no charges to this. They are sharing the electrons between each other to form a compound. Also, ionics typically form a crystal lattice, a repeatable pattern, and they are crystals a lot of the times in nature. Where molecular compounds, they're the true number of atoms in a formula, and they can form crystalline-like structures. Sugar is a molecular compound. It forms kind of a crystal-like structure due to how it's processed. In nature, though, sugarcane is a plant, so it's kind of moving up and down the plant to transport water and other things. So it's not in the form of a crystal lattice that's rigid with positive and negatives like an ionic compound. Molecules are the smallest unchanged individual unit of a compound formed with two or more atoms that are nonmetals, and a molecule cannot be further divided without destroying its identity. So, like here, we've got water. If we separate the hydrogen from the oxygen, it's no longer water. It's two volatile gases. Hydrogen, which is highly flammable, and so is oxygen. Ions, again, like I said, you had Na plus and the Cl negative. Metals tend to form positive charge ions called cations. Nonmetals tend to form negatively charged ions called anions. Here's like an example of different compounds that can have the same elements but be radically different. Here we have H2O2 and H2O. We have water and hydrogen peroxide. One you drink, the other one you don't want to drink it, but you can use it on your toothbrush to whiten your teeth. You can put it on cuts to sterilize. Pure hydrogen peroxide is a slight pale blue, just really light blue. The boiling points, hydrogen peroxide is slightly higher, and the density is also slightly higher. So same two elements, but radically different properties. Now, formula of compounds tell you how many of each type of atom are in the compound. So it has the example of sulfuric acid. Sulfuric acid is H2SO4. That means it has 2 hydrogens, 1 sulfur, and 4 atoms. So you might think you could just put, HHS and then 4 oxygens. But we actually pair those up, and we have hydrogen here that is bonded to a sulfate ion. Here's like the breakdown of the parts of a chemical formula. You've got the individual elemental symbols that indicate that element is in the compound. You've got what's called subscript numbers that tell you how many of that particular atom are in the compound. You also, they are also written a certain way. Typically metals come first if they're bonded to anything. That's kind of a hard, fast rule. If it's hydrogen that is written first, hydrogen can act like a metal and a nonmetal. It acts like a metal because it can form a positive 1 charge even though it's a non-metal. That's what's special about hydrogen. Hydrogen is very versatile to what it can bond with, and also by how it can go from a positive charge to a neutral charge to a negative 1 charge depending on what it's bonded to. So if we have something that has what's called a polyatomic ion, so sulfate, SO4, is a polyatomic ion. If we have a polyatomic ion and we actually need more than one, we put parentheses around the polyatomic ion and then put a subscript outside of those parentheses as a subscript to indicate how many of those polyatomics I need to balance out the overall reaction, or the overall compound. I apologize. So again, pause the video to practice this, and then you will, before you see the answer. Alright, so how would you read the following formulas? You've got sodium and chlorine, magnesium and an oxygen, barium, and this is a polyatomic ion of nitrate, and then C2H6O. So, and you don't want to use common names. Some of you might know that this is NaCl is salt, but it's actually sodium chloride. This would be magnesium oxide, barium nitrate, and this actually has an organic name. This is a type of sugar. Okay, so in your naming and formula writing, we're going to be dealing with what's called inorganic names. Simple metal to nonmetal, and simple metal to polyatomic ions. And there's a third one called complex metal, which has multiple charges to either a nonmetal or a polyatomic ion. So how do we calculate composition of compounds? Well, we know there's 2 hydrogens and 1 oxygen in water, and 2 hydrogens and 2 oxygens in hydrogen peroxide. Well, what we do is, well, it's a percent. It's part divided by whole times 100. So we have we have 3 atoms here, 2 of hydrogen and 1 of oxygen. 2 plus 1 is 3. Okay, then, and you can't just say, oh, okay, 2 divided by 3, that's going to give me the percent of hydrogen. You have to consider the mass. Hydrogen's mass is way less than oxygen. Oxygen has a mass of 16, where hydrogen has a mass of 1.01. So we've got to take the masses of hydrogen and add them to oxygen. That's our total mass, and that happens to be 18.02 grams per mole. So we take 2.02 grams and divide it by the total, and we get, out of the mass, only 11% of the mass is hydrogen. 16 divided by 18.02, which is the total mass of water, gives us 88%. So you have to realize the law of definite composition states that a compound has to have 2 or more atoms or elements. They need to be chemically combined, and they're definite proportion by mass. In other words, I can't have 127% of 5 elements. It has to be up to 100%. Can't go over 100%, and you're taking the part divided by the whole in regards to finding molar mass of the whole, and then the mass of the individual part, and then dividing those two. All right, now law of multiple proportions talks about you could have the same 2 elements and have different formulas for them. Now the first example here is copper 1 and copper 2 chloride. Copper 1 chloride is indicative of the charge. Copper 2 chloride says that the 2 is the charge on this copper. So copper can have 2 different charges. Now, copper 1 chloride there's only one copper to one chloride because chlorine, that changes to chloride, has a -1 charge. So we have +1 on the copper 1 and then -1 on the chlorine atom, which means 1 plus 1. 1 plus -1 equals 0. All of your formula writing, you have to make sure that the entire compound adds up to 0 on its positives and its negatives. If it doesn't, then it's not chemically neutral and it's not feasible to be stable. So chlorine has a -1 charge, but now I have copper 2. That means a +2 on the copper, which means I need 2 chlorines. So I put a subscript of 2 after the chlorine to signify that I need to cancel out that +2 of the copper. Methane, you've got CH4. So again, you add up the total mass. Mass of carbon divided by the total mass times 100 gives us 74.9. And then 4.04 divided by the total mass gives us 25%. And there's other examples there. Feel free to pause the video. Laws and theories, we talked about this in Chapter 1 about what a law, what a theory, and a hypothesis is. So I'm not going to review this. And there's the learning objectives as far as the end of the chapter. In class, I will be doing more practice with you on 3.3 to help you learn chemical formula writing. What I need you to do is to make sure that you know the symbols and names of the periodic table of elements. So please practice those games. And I'll see you in class.